Hi folks, this is Linear Algebra Checkpoint Quiz 2. We're given a new definition. Let A be an n by n matrix. We're defining the trace of A to be this sum. And a lot of times with summation notation, when in doubt, write it out. So what is this equal to? When I equals 1, AII is A11. When I equals 2, it's A22. And this continues up to n, ANN. So what we're doing is we're adding up the entries along the diagonal. So in number 1, we're asked to find the trace of this specific matrix. So that's going to be A11 plus A22 plus A33, because it's a 3 by 3 matrix. A11 is 1, A22 is 7, A33 is 8. So as you can see, we're just adding up the diagonal entries. And you add that up and you get 16. So the trace of that matrix is 16. Okay, number 2, we're asked to prove some properties about the trace. And so I'm going to keep up here our definition again. So the trace of A is the trace of Aij. That was a sum I equal 1 to n, AII. Well, we're assuming, of course, A is an n by n matrix. So, property A. We're to let A and B be two generic n by n matrices, and we're supposed to prove that the trace of the sum of the two matrices is the sum of the traces. And so, as always in these proofs, we're just going to start off with A and write it Aij, and B as Bij, two generic n by n matrices. And we're just going to start and compute this and then compare it to what we get there. So if I want the trace of the matrix A plus B, that's the trace of the matrix Aij plus the matrix Bij. So we're taking it back down to elements. And the definition of matrix addition says this is the trace of the matrix Aij plus Bij. Alright, so remember, with matrix addition, the Ij entry of the sum is the sum of the Ij entries of these two. So this is what's happening in the Ij entry of the sum. Now how do we get the trace of an n by n matrix? Well, according to the definition, we sum up the n diagonal entries. What are the diagonal entries? It's where I and j are the same. The diagonal entries of the sum come from adding the diagonal entries of each individual piece. And so this is going to be Aii plus Bii. Right? That's how we get the Ij entry, is we set the II entry is we set I equal to j. So that's the trace of A plus B. Now we need to compare it to the trace of A plus the trace of B. So what's the trace of A plus the trace of B? So that's the trace of the matrix Aij plus the trace of the matrix Bij. By definition, what's the trace of the matrix Aij? It's the sum I equal 1 to n, Aii. The definition of the trace of Bij, that's the sum I equal 1 to n, Bii. And so now I compare these two sums. Well, this is property of summation, which is really just the associativity and commutativity of regular plain old real number addition. So we can say since the summation I equal 1 to n Aii plus Bii is the same as the sum I equal 1 to n Aii plus the sum I equal 1 to n Bii, we have the answer. The trace of A plus B is in fact the same as the trace of A plus the trace of B. And that's what we wanted to show. So that'll do it for 2A. In B now we're asked to show that the trace of k times A, where k is a scalar, is the same as k times the trace of a. So this is for all real numbers k. So how do we begin? We start off with the trace of k times a. That's the trace of k times the matrix aij. The definition of scalar multiplication says I take k times each of those entries. And the definition of trace says I add up now the diagonal entries. So what are the diagonal entries? That's where the I and the j are the same. So that's the trace of k times the matrix A. What I need to do now is compare that to k times the trace of A. So k times the trace of A is k times the trace of the matrix aij. And by the definition of trace, that's the sum I equal 1 to n of aii. So we're adding up the diagonal entries. And so now I just need to compare what I have here to what I have here. And basically, these are equal because of the distributive property. So since the sum I equal 1 to n of k a I equals k times the sum I equal 1 to n aii, we get that the trace of k times a is k times the trace of a, which is what we wanted to show. So that'll do it for part B. For part C, we're asked to look at the trace of the transpose and show that that's the same as the trace of the original. Now remember what the transpose is you're taking all the rows and making them the columns. So in a square n by n matrix, what's going to be the same in that is going to be the diagonal. So that's really what's happening here. So what do? We start off with the trace of a transpose and work out what that should be. So this is the trace of the matrix aij transpose, which is the trace of aij transpose. And what we do is we interchange the I and the j. So this is the trace of the matrix aji. So the ij entry of the transpose is the ji element of A. And now when we take the trace of this, we still set I and j equal. The sum I goes from 1 to n, aii. And that's exactly what the trace of A is. That's the trace of the matrix aij, and which by definition is the sum I equal 1 to n. We set the I and the j equal. So hence, the trace of the transpose is the same as the trace of the original. You may wonder how the trace behaves under matrix multiplication. Well, that's take home 2. This will do it for checkpoint quiz 2.